I welcome all of you in the fifth session of International Conference on Next Generation Innovations in Computer Science, AI, and Mathematical Sciences, organized by Shankarlal Khandelwal Arts, Science, and Commerce College, Akola. Friends, we have Honorable Professor Rupali Kale Madam, Head Department of Computer Science, Sri Shivaji College, Akola, as a chairperson, and Honorable Dr. Dipesh Kumar Patel, Sir, Assistant Professor, Department of Mathematics, Vishweshwaraya National Institute of Technology, Nagpur, as an invited speaker. It is my immense pleasure to introduce our chairperson to you all. Honorable Professor Rupali Kale Madam is serving as a head Department of Computer Science in Sri Shivaji College, Akola. After completing her post graduation in computer science and NET, SET, and GATE examinations successfully, she joined as a head of the Department of Computer Science, Sri Shivaji College, Akola. She is pursuing her PhD in research area, image processing, and deep learning. She has published 10 research papers in national and international journal of repute and presented papers at various national and international conferences. She is a winner of Color Coat at university level Avishkar 2025 and she is honored with the Best Teacher Award. She is a master trainer for MSD EED means MSD and MSFDA initiatives and trained about 100 teachers and students. She guided 21 postgraduate and 50 undergraduate students in successful project completion and an active member of various college and university committees contributing to academic and administrative excellence. I request Dr. Archana Khandelwal Madam to welcome and felicitate her. Thank you, ma'am. It is my proud privilege to introduce our invited speaker for the fifth session of this conference, Honorable Dr. Dipesh Kumar Patel, sir. He has 15 years of experience in the field of education. Now he is serving as an assistant professor, Department of Mathematics, Vishweshwaraya National Institute of Technology, Nagpur. Previously, he served as a lecturer at Department of Mathematics, Dr. C.V. Raman University, Kagi Road, Kota, Bilaspur, research scholar at Department of Applied Mathematics and Humanities, Sardar Vallabhbhai National Institute of Technology, Surat, and an assistant professor in Development Department of Applied Science and Humanities, GIDC Degree Engineering College, Abrama, Navsari, Gujarat. He has completed his PhD on fixed point theory in 2009 from Government ERRPG Science College, Bilaspur, Chhattisgarh, India. He has completed the research project sanctioned by NBHM in June 2017 on existence of uniqueness problem arise in operator equations and inclusions. He is a life member of Indian Mathematical Society and Indian Science Congress Association. 4 students had completed their PhD and 2 students are pursuing their PhD under his guidance. 14 PG students have successfully submitted their research dissertation under his guidance. They participated in 29 conferences, school training programs, workshops, and seminars, published 3 books chapters, and his 34 papers, research papers, are published in national and international journal of repute. I request Honorable Kale Madam to please welcome and felicitate him. Thank you, ma'am. Now I request our invited speaker, Honorable Dr. Patel sir, to guide us. His topic is recent developments in fixed point theory and its application. Sir, please.
For introducing. Respected Principal Sir, Dr. J.M. Sabu Sir, our today this convener of this program. This is hello, 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 working. Hello, 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 hi, hello. Yes. Respected our respected Principal Sir, Dr. J.M. Sabu Sir. Okay, okay. Thank you. Thanks. Convener of this program, Dr. Petkar Madam, organizing secretary Dr. Revaskar sir and Suratkar sir. Thank you for inviting me for this 2 days program of international conference on computer next generation innovation in computer science, AI, and mathematical science. Uh, Today, in mathematical science, I will highlight some topics on fixed point theory, and I will try to highlight some highlights on development on the metrical fixed point theory and its development with some applications. Let me share the screen of the presentation. So I'll try to highlight some recent developments in the fixed point theory and its applications. The topic is very vast and vast area of the research in mathematics, and it has a very nice applications in not only in mathematics, in various other branches of engineering and science. So first I will explain what is the fixed point. I think many of us are familiar about the meaning of the fixed point. If x is a non-empty set and f is a mapping from x to x, which is a self mapping, then a point of x naught is said to be a fixed point of f if and only if x naught is equal to x naught. If the mapping maps the point to itself, then x naught is called fixed point. By looking this one function fx equal to root of 2x, we can tell about the fixed point of this f. Here geometrically we can say that if the curve of this function root of 2x will intersect the line y equal to x, then the intersection points are the fixed point of this function fx. So in this function, this curve is intersecting at the 2 points of the line y equal to x. The 2 points are here. One is the origin and second is the second intersection point is the point 2. So in this curve, the function has two fixed points, 0 and 2. These are some examples where we can tell us about some fixed point of the mapping. If a mapping is a real line to real line, then first example is f of x equal to x plus 1. In this example, we can say that there is no any fixed point of the mapping f, because no any x is satisfying the definition of fixed point f x equal to x. In the second case, f x equal to x identity mapping, then every point of the real line are the here fixed point of the mapping f. Third example, here x plus x minus 1 into x minus 2 into x minus 3. Then in this example, the mapping has three fixed point 1, 2 and 3 in the real line, because all these 3 points are satisfying the x now fx equal to x definition of fixed point. In the next example 4, function is x by 2, then f has exactly one fixed point, only 0 is here satisfying the definition of fixed point. And one more example, in this example we can see that here if we consider this type of discontinuous mapping, then this mapping has also infinite number of fixed point, even it is a discontinuous mapping. The discontinuity point is here point 0. So in this example, we are observing that there are possibilities. The mapping may have a one fixed point, more than one fixed point, or may have infinite number of fixed point, or mapping doesn't have also any fixed point. So there are various possibilities. Consider again the function f from R to R, which is one continuous function. These two type of functions are here one example of continuous function, but this function don't have a fixed point. This then we say the function is a fixed point free map. And instead of this, here note that this function f, these two functions f are not bounded function. So if the function is not bounded, even it is continuous, then there is a no any guarantee of existence of the fixed point. If you consider the function as a bounded function, then there always is a fixed point x of r, such that it satisfies x equal to fx. Because in this case, the function x minus fx, if we consider it as a gx, then this x minus fx must change the sign at least once in the real line. And because it's changed the sign in the real line and it is a bounded function and continuous, so therefore, because of the intermediate value theorem, there is a guarantee of existence of one point in the domain and which attains the 0. So suppose gx is attaining the point 0, that means x minus fx is there 0, so that is equivalent to x equal to fx. So therefore the function, if it has it is bounded function, then it has a always a fixed point. This function f is here function from 0 1 to 0 1, and which is a continuous function. So here we can say that it is a bounded function defined on this interval. And here this gx x minus fx is changing its sign in the real line, and so therefore it will attend, and hence the function is f has a fixed point, because gx equal to 0 means there g 0 equal to 0, instead of here we have a gx equal to 0 and it is equal to x minus fx equal to 0. So therefore f has a fixed point. We can say that the interval 0 1, which is a one bounded interval, this interval 0 1 has a fixed point property with respect to the continuous mapping. Not only this interval, we can say that as a subset of R, it has a wider class of continuous mapping which has the fixed points. And not only the interval 0 1, any other interval instead of 0 1, any other interval a comma b, if we take mapping from AB to AB, then always this mapping has a fixed point property for any AB of the real line. These the first result was observed by the and given by the Brouwer, and it is a very famous theorem. Brouwer fixed point theorem tells us about this structure. If we have a closed unit ball, now instead of interval, this result is generalized for any finite dimensional space. Finite dimensional space, and a closed ball Bn is supposed there, and mapping T is from ball to this ball, and it is a one continuous mapping, then this T has a fixed point in this ball. So we can see that this is a generalization of the that previous result from interval to any unit ball be an up in finite dimensional space. Or if instead of this ball, if we take a subset K of Rn, a, a compact and convex subset, then also any continuous map from K to K has also a fixed point. So the proof of this theorem we can see by this simple proof of Brouwer theorem here I am presenting, that is used by this lemma. There is one lemma. This lemma says that there is no any continuous mapping G from B2 to S1 such that Gx equal to x for every x belonging to S1. B2 is here we are taking example n equal to 2. That means we are on R cross R xy plane, and B2 is here one disk, and S1 is here one circle, unit circle centered at suppose 0. Then this lemma says that there is no any function G from this disk to this circle such that Gx equal to x. And if we assume in the proof of the theorem, if we assume the mapping f which is from B2 to B2, if we assume the mapping has no any fixed point, then then suppose the mapping has no any fixed point, that means suppose x is not mapped to x itself, so fx is not equal to x, so therefore there will be some distance between x and fx, and these two are different point. Now if we join this 2 point x and fx by a straight line, then this straight line cross this circle at the boundaries, and we can say that the point x is always mapped to this boundary point, and we can define a mapping G which will be a continuous mapping, and this continuous mapping G is always fixing the boundary points. So this mapping G which is a continuous mapping, and it has now a fixed point which is it's a boundary point. So therefore it is a one contradiction of the previous lemma. But lemma is saying that there is no any continuous mapping G from B2 to S1 which has a fixed point. So whenever we assume there is no any fixed point of f, then it is a contradicting that lemma, that result. So therefore the mapping f has a fixed point. There are many applications of the Brouwer fixed point theorem. One application here, uh, we can show the existence of the Perron eigenvalue of and eigenvectors of a matrix. Suppose A is a square matrix of order n with all its coefficients are positive. That is it is a one positive matrix. Then A has positive eigenvectors, positive eigenvalues with an associated eigenvectors whose components are all positive as well. So this existence of the eigenvalue and eigenvectors we can show by the we by using the Brouwer fixed point theorem. For that purpose, here if we consider a subset K of Rn, it is containing all those x. X is a one element of Rn. If we collect all those element of Rn whose components are greater than or equal to 0, and such that the summation of all the component is equal to 1, then this collection which is a subset of Rn, this is a one compact convex subset of Rn. And suppose if there exists x naught in this case such that Ax not equal to 0, then our by definition of eigenvalue eigenvector 0 become our fixed 0 become our eigenvalue. And if we assume suppose this is not here happening for all x belonging to K, that means this summation is always a positive number, and it is a positive minimum inside this K. And if we define a mapping from this compact convex subset K to K by this way, whose components are here, f is a mapping from nth dimensional space to nth dimensional, whose components are here defined by fi x, then this f has f is a continuous mapping because all components are continuous. So therefore by using the Brouwer fixed point theorem, this mapping f has a fixed point x naught inside K, and therefore A x naught equal to lambda x naught. This is screen down. Okay. This example here is in if we take if we discuss the Brouwer fixed point theorem in one infinite dimensional space L2. L2 is here the sequence space. In this space, if we consider a closed ball and a mapping continuous mapping T from B to B, which is defined by this Tx equal to root of 1 minus norm of x square comma x1 comma x2 comma x3, then this mapping T, which is continuous mapping from B to B, but this mapping has no any fixed point because there is no any point in the this B which is mapped to itself. So this example is saying that the Brouwer fixed point theorem uh, we cannot say it is true. It holds if we consider the one infinite dimensional space like L2. So how we can say that this ball version of the Brouwer fixed point theorem doesn't hold. Even the convex version of the Brouwer fixed point theorem, there is a chance it holds. So therefore, Brouwer fixed point theorem is not true for infinite dimensional case. So Sauder, by observing this, Sauder in 1930 proved the one fixed point theorem for infinite dimensional case by using the concept of compact operator. If X is a one real Banach space and let K be a subset of X, which is now a compact and convex subset, and if T is a continuous mapping from K to K, then this T has a one fixed point. So there are two versions. One is related to this here is space K is a one compact and convex subset and T is a continuous mapping. In the second version, if we consider T as a compact operator, then also if T is a compact operator and space K is non-empty closed and bounded convex subset of Banach space X, then also T has at least one fixed point. So these two versions are Sauder theorems. This is one simple application of the Sauder theorem. That theorem can be applied to discuss the existence of the solutions of this boundary value problem. The boundary value problem one, we can convert as its equivalent integral equation, which is here given by number 2, and by using by defining one operator T, uh, by defining one operator T like this, define the operator T from this is ball BR to BR by TXB equal to, that is here number 3. Define this operator T. Then this operator T is a one operator which is satisfying this order fixed point theorem, and because of that it has a one solution. So existence of the fixed point of this operator is here equivalent to existence of the solution for this boundary value problem. That I will also tell also show in the next slides how the fixed point problems we convert, how the given problem we convert as a fixed point problem, and the we apply some fixed point results, and then we can say about the existence of the solution of that problems. If we observe these simple equations x square equal to 1, then this x square equal to 1, and we want to find the roots of this equation, then there are some simple methods. Two methods are here. By using the some substitution or guessing, we can say about the roots of this equation x square equal to 1, or by factorizing the given equation we can say about the roots. We have so many formula for this quadratic equation. We have this formula. By using this formula we can tell about the roots, or by plotting its graph if possible, then we can tell about its root. So not only this few, there are many other methods for finding the roots of some equations. Instead of this simple equation, if we have this type of equation x square equal to cos x, that means we have some transcendental equations. That time there are few methods available. Some methods are here: bisection methods, Newton Raphson methods, and we have also fixed point methods. So by applying the fixed point methods, we can solve this equation also. by this is by using the some iteration we can, all these methods are based on some iterations based. So in fixed point method also we have some iteration which is defined by the Picard. In 1893, Picard observed one iteration, defined one iteration xn equal to f of xn minus 1. That is a very famous iteration. By name, it is Picard iteration. So he also give one convergence theorem for this iteration. That is Picard convergence theorem. If the mapping f is a one mapping from AB to AB, and which is satisfying continuity and differentiability in these intervals, continuous on closed interval AB, and it is differentiable on open interval AB. And if there exists a one number m such that the modulus of f prime x is less than or equal to m, and this m is strictly less than 1, then this sequence, which is known as the Picard sequence, this sequence xn plus 1 equal to fxn converges to the fixed point of the mapping f. This sequence xn is called Picard iteration, or also called Richardson sequence. So this is the one convergence result for the Picard iteration. This iteration, by using this Picard iteration, we can also find the root of some equation. For example, again, if you consider this, this is the same convergence theorem. If we want to find a solution of this, solution means root of this equation cos square x minus 3x equal to 0, then what we do to apply the Picard iteration? First we rewrite the given equation in form of tx equal to x by arranging this equation. So here we will write x equal to first cos square x upon 3, and we will assume that this we will try to show that this t is here satisfying the that convergence theorem. So to check the difference modulus of this t prime, the modulus of this is here coming that, and it is less than or equal to 2 by 3, so which is strictly less than 1. So therefore we can say that by using the above convergence theorem, previous convergence theorem, there is a unique solution of the this function, this equation fx equal to 0 on this interval 0 1. Solution we are here not finding. The solution we can find by applying the this iteration. Here this is guaranteeing that the equation has a one root. So to get the solution, we can apply the iteration. The iteration is here. Picard iteration is here xn equal to cos square xn minus 1 upon 3. And the iteration wherever it converges, that will be the solution of that equation. In 1922, using the Picard iteration, the Banach has given a very famous theorem that is known as the Banach contradiction principle. The theorem says that if we consider a mapping F on a complete metric space, and which satisfies this condition d of fx fy less than or equal to k dxy, where k is a one number between 0 and 1, strictly less than 1, then the mapping F has always a unique fixed point, and this and the related Picard iteration will converge to the this fixed point for any initial point x naught of this space x. So there are very large number of application of this Picard Banach convergence theorem, and to apply that theorem, to apply this theorem in any mathematical problem, we convert that problem. Suppose the problem is fx equal to 0, then if we convert this problem as a fixed point problem, which is here given by fx equal to x, and this, and then we try to apply the Banach fixed point theorem, and we get the fixed point of this equation fx equal to x. This mapping is small f, and this is, suppose x star is the fixed point, then this x star becomes the solution of that problem, and the iteration also converts to the this fixed point. We can also discuss the stability of the our solution. Here, one simple application of the Banach contradiction principle is here in this slide. If we consider the Freedom integral equation, which is the equation number 6, Freedom integral equation, where the integral limits are from a to b, then this integral equation we can discuss its solution. solution exist or not exist, or unique or not unique. So if it satisfy the, by using how we use the Banach fixed point theorem, and we can uh, say the existence of the solution. So here the solution will be one function. So that's why we are considering the space C01, which is the space of all continuous function defined on the interval AB. The metric in the C01 is here. C01 is not that one infinite dimensional space. The metric is here defined by this maximum number, equation number 7 is here the metric inside the, in this space C01. And uh, this kernel of the equation 6 is here suppose bounded by a number C. Then here we are defining an operator T, a fixed point operator T from CAB to CAB by this equation number 9. T of xt is mapped to mu t plus mu into that integration. Then we will show that this T is satisfying the Banach fixed point theorem. That means T is contractive. This T is contraction. The contraction means this condition uh, in the definition and in the theorem of Picard, this number B, equation number B, d of fxy, fx comma fy is less than or equal to k dxy, this is called contraction, contractive condition. So here for this mapping T, if we will, so that this T is a one contraction in this space CAB, and CAB is a one complete metric space with respect to this metric D. So that's why the Picard Banach fixed point theorem holds, and the mapping T has a one fixed point, and that fixed point become, that fixed point means here it is a one function, and that function become a solution of that integral equation, Fredholm integral equation. Here this is the one detailed calculation of the how we can show that it is a one contractive mapping. So this is instead of k, here we are getting that mu into this number, mu norm of mu into c into this maximum. This is coming as a constant k. And the solution function we can obtain by using again the Picard iteration. The wherever the iteration converge, that converge converging point will be a fixed point, and that will be also solution of our Fredholm integral equation. This is one example. Here one example related to Fredholm integral equation, and because of this c is, which is the maximum of this c is coming here 2 into, after some calculation we can easily find that this c is coming 2 into e to the power 1 by 2 minus 1, and that's why mod of mu is less than 1 by this quantity, and hence overall it is strictly less than 1. The constant here is coming less than 1. This constant is coming less than 1. Liebniz constant is less than 1, therefore it is satisfying the Banach fixed point theorem. So it has a one solution. There are different approach to find out the solution. Here it is guaranteeing that the Fredholm integral equation has a one solution. Solution exists and it will be unique. We can also apply the Banach fixed point theorem for any nonlinear integral equations like that. Suppose one equation number 10 is a one form of one nonlinear equation with this kernel k, and equation 11 is uh, involving a operator t, which is a fixed point operator. We will show that this t is satisfying the Banach fixed point theorem, and so we can apply this type of integral equation. It's we can discuss its a solution exist or not, and if exists then unique or not. We can also apply the Banach fixed point theorem for solving the, for discussing the existence of the solution of Volta integral equations. Here this equation 12 is a one Volta integral equation, and if this integral equation where the kernel k is from AB cross R to R, which is one continuous mapping, and if this k satisfy this condition, which is called Liebniz condition on the for the k, modulus of k s us minus k s vs is less than or equal to L in L, which is here L into modulus of us minus vs. Then this whenever this L is between less than or equal to, L is less than or equal to alpha for all s belonging to the involved interval I, then the integral equation 12 has a unique solution in this CIR. CIR is the here set of all continuous function defined from the interval I to R. So Volta integral, the solution exists or not exists, that can be also discussed by using the Banach fixed point theorem. Similarly, suppose we have one initial value problem where du by dt equal to k tu. K is here a function which is a suppose continuous function, that is called this problem number 15 is called uh, 13 is called Cauchy integral equation, and this is the existence theorem for this initial value problem. Here, if this k is satisfying this Lipage condition, and then we have we can say about the existence of the solution of this initial value problem. Here, what we are doing, we can convert this initial value problem to its equivalent integral equation. That is the equation number 14. The equation number 14 is one Volta integral equation. Note that this Volta integral equation we have that in 12. Here the lower limit is just instead of a, we can also use for any other uh, point in between point. So here this is coming t naught to t. So this 14 is also a one Volta integral equation, and we can discuss the solution of this Volta integral equation. Whatever the function will satisfy this equation will be the solution of our problem number 13. So solution of initial value problem also we can discuss, and this is the existence theorem for that. Coming to the development on the fixed point results, there are many directions uh, where the mathematician have improved the Banach fixed point theorem. So one of the direction is here generalizing the or introducing the other types of contractive conditions instead of the contractive conditions involved in the Banach fixed point theorem. There are many other contractive definitions. So generalization of other contractive type conditions. I am listing here some of the contractive conditions which are famous in the literature. Banach contractive conditions is here instead of contractive condition. Here, if equation number 15, which is one condition, this condition is used by the Kanan in 1969. Kanan used this condition, and he shows that this condition is also applicable for discontinuous mapping. Note that Banach fixed point theorem is only applicable for continuous mapping because that condition is implying the continuity of the mapping F. Contraction implies the continuity of F, but this 15 is here requiring not continuity. So uh, uh, we can also discuss the existence of the fixed point for discontinuous type of mapping. So that's why this Kanan fixed point theorem is has its own importance. And later on, it was also by Subramaniam, it was also correct proved that the Kanan theorems can be correct. Kanan's theorem characterize the metric completeness also. That means a space X is complete if and only if every Kanan mapping on the space X has a fixed point. So it has its own importance because first time this condition can be used for discontinuous mapping. Then Reach has introduced this condition number 16, where the right hand side is replaced by right hand side in the Banach was k into dxy. Here right hand side is replaced by sum of these three quantity q into dxy plus r into dxfx plus s into dyfy. And uh, Rich also proved some one fixed point theorem. The right hand side is further replaced by this quantity k into xfy plus y dyfx. So this is also by using this condition, Chatterjee also proved one fixed point theorem in 1972. After that, Serig replaced this right hand side by the sum of this four quantity q dx y plus r dx fx plus s into dy fy plus the sum of other this to t into this 18 number equation condition number 18. And he also proved one fixed point theorem, so obtaining the fixed point of this mapping F. Then later on, James Frisky replaced the right hand side by maximum of this three quantity and proved and obtained one fixed point theorem. So these are the time to time the improvements on the Banach fixed point theorems by replacing the contractive definitions. Hardy and Roger used the right hand side, this five terms alpha dxy plus alpha 1 dxy plus alpha 2 dxfx plus alpha 3 yfy plus alpha 4 dxfy, and last term is containing yfx. So combination of all these five of terms, and he also proved one fixed point of the mapping F. What Sirik did, Sirik replaced the right hand side of the Banach fixed point theorem, Banach contractive condition, by this maximum of these five quantities, and obtained the fixed point of the mapping F. So this Sirik till 1974, the Sirik was the most generalized form of among all the contractive conditions because it covered the many previous contractive definitions. Here, in this implication diagram, uh, there how the which contractive condition is generalized of the previous one. This is one comparative diagram. The Sirik is containing Sirik is generalized among all the previous contractive conditions, but still there are hopes to get some new contractive definitions. And in one of the article in 1977, there is one famous paper Rhodes by the B.E. Rhodes, where he compared around 125 type of contractive conditions in his article. There is a very nice comparative study on this 125 contractive conditions till 1977. Next direction, to improve the contractive conditions by using some control function instead of the contractive condition. What type of control functions like this? In 1968, Borden Wong has defined this condition number 22, where right hand side is replaced by a function of dxy, where psi is a one upper semi-continuous function from right and satisfies this psi t is less than t and greater than or equal to 0. Then also the mapping may have the mapping has a one fixed point. This psi, if we consider psi t equal to kt as in particular example of the psi, then it contains the Banach contractive conditions. Then Garethi replaced this right hand side instead of one constant. He took alpha dxy in place of the k, and this alpha is here. Alpha range is here lying in the interval 0 1, and alpha is satisfying that t alpha of tn is 10 to 1 whenever alpha tn is tending to 1 implies tn tends to 0, and alpha t equal to k, then it also contains the Banach contractive conditions. Later on, Matkowski replaced the right hand side by again another function, control function psi. This psi is here satisfying, which is the mapping from 0 1 to 0 1, and it is a one monotone non-decreasing mapping, and limit of this psi n is equal to 0 as n tends to infinity for all positive t. Then the function f has also a fixed point in a complete metric space. All reals are in the complete metric space. As a particular case, if psi t equal to kt, then this psi it equal to kt, then also the mapping f has a fixed point. And mapping has a fixed point, and it contains the Banach contractive condition. The next weak contractive condition was introduced in 1997 by Albert et al. And this was defined in the Hilbert space, and later on the same definition was also given in the metric space by the Rhodes in his article. And they also proved some fixed point theorems in the complete metric space. How the main motivation for getting the defining the weak contractive condition is here in Banach fixed point theorem. Banach contractive condition number, that is the condition number 25. The right hand side is k into dxy. The right hand side in 25 we can write dxy minus L time dxy, where L is suppose 1 minus k. Then this is just an arrangement, but using this idea, further L can be replaced by a function of dxy, and this is here. This condition 27 is used to define the weak contractive condition, where this phi is a function from 0 infinity to 0 infinity, which is one continuous mapping and non-decreasing function satisfying psi t equal to 0. Then if and only if t equal to 0, then using this 27 they obtain some fixed point theorems. This function phi is famous in the literature by name altering distance function. psi t equal to 1 minus kt as in particular example, then we get again the Banach contraction contractive conditions. So all these conditions which are used by one control function, so all these conditions are covering the our Banach contractive conditions. Further, the 28 was introduced by Datta and Chaudhary in 2028, where phi and psi are psi are two altering distances functions, and then this if particular phi t equal to t and psi t equal to 1 minus kt, then they cover the contractive conditions. So till 2008, and after that there are many other also in the literature. There by given some contractive conditions are given by some mathematicians, some researchers by using some control functions. And in 2012, Jelly and Jelly et al. They have given some contractive conditions. Rai contraction is also famous in literature. In 2015, Karpinar has given some conditions. So there are many other contractive conditions, and this is one comparative study among all that. But still, there are hope to get some new contractive conditions by using other type of control functions. This theorem is also famous in the literature, Suzuki fixed point theorem. Suzuki defined one mapping theta, and using this theta, he defined one contractive condition. Whenever this theta are into df x f x is less than or equal to dxy, then we have the condition dfx fy less than or equal to r dxy. So using this condition, also we can get one fixed point result. And this theta r is the best uh, constant for every r belonging to 0 1, and that is here proved by the Suzuki in his article. This is one example related to Suzuki theorem. F is here satisfying. This is a one space X containing all these 5 points, and in this space F is satisfying that Suzuki condition, this condition, and this is also a complete metric space. So this F has a one fixed point here. Later on, by uh, Samet, one contractive definition was introduced by using the two function alpha and psi, and he gave the definition of alpha psi contractive conditions. The condition is here alpha f x y into dx f x f y less than or equal to psi dxy, and this alpha is here one mapping from x cross x to 0 infinity, and psi is here mapping from 0 infinity to 0 infinity, satisfying that summation of psi and t is less than finite. So if we use the alpha admissibility property, which is here in the definition, next line, f is alpha admissible if satisfy if alpha x y less than greater than or equal to 1 implies alpha f x f y greater than or equal to 1. Then this uh, if f is one alpha psi contractive condition, that is in the next theorem. If f is a one mapping from x to x, and it is one alpha psi contractive condition mapping, and if f is satisfying the alpha admissibility property, and condition number 2 and 3 continuity, and there exists a point x naught such that alpha x naught f x naught is greater than or equal to 1, then also f has a one fixed point in the space x. So this is a one famous contractive definition, alpha psi contractive condition. Later on, next f contraction is here introduced by Rodowsky in 2012. He also considered one function f. F is a one function which satisfy these three conditions, number f1, f2, and f3, and the contraction 29 is here called f contraction. Whenever d of fx fy is greater than 0, then it implies tau plus f of d of fx fy is less than or equal to f of dxy. So here it is by using this condition 29, Wadowski proved a one fixed point theorem. And when here this tau is a one strictly greater than 0 number. As a particular case, if we consider f of alpha equal to log alpha, this function, then then every f contraction satisfy this dfxy less than or equal to e to the power minus tau dxy. That means we get a Banach contractive condition. Further, Khojaste in 2015 introduced one new contractive condition by using one another function zeta. Zeta is here in his paper. He mentioned the name of this zeta is simulation function. So using the simulation function is a function which satisfy these three conditions: zeta 1, zeta 2, zeta 3. And using this condition, number 30, he defined this condition number 30, and he also obtained one fixed point theorem that is called jet contraction in the literature. Condition 30 is called jet contraction. And if we take the we can say that because of the property number zeta 1, always every jet contraction are one contractive condition. Any mapping F which satisfy jet contraction is always a contractive mapping. So they also show that every jet contraction is contractive in their paper. And in complete metric space, this jet contraction has a fixed point. On the other hand side, these two definitions are already available that time in the literature. These definitions, Krodowski measure of non-compactness was defined in 1930 by Krodowski, and next definition is the Hausdorff measure of non-compactness. So these two are the function from first is the function from chi. First is the function chi from Vx to 0 infinity. Vx is the set of all the bounded subsets of the space X, and chi is a function from Bx to 0 infinity defined by this chi r. Chi r is the infimum of all the tau such that r is covered by this Si, such that diameter of Si is less than or equal to that number tau, and infimum of all such tau is here one our chi r, that we will call Koskowski measure of non-compactness. So this is similarly alpha s, which is Hausdorff measure of non-compactness. This is also one infimum. So these two are the measure of non-compactness famous in the literature. And this using these two, there are some fixed point theorems given by some researchers. These two measure of non-compactness satisfies these common properties. Both of them satisfy these properties: regularity, invariance under passage, and monotonicity, maximum property, invariance under passage to the convex hull, algebraic subadditivity, semi-homogeneity. And number H is here, we can say it is one generalized form of the Cantor intersection theorem. So in using this property of this two measure of non-compactness, this is the first function psi is here one example of the measure of non-compactness. But the second example phi m, this is not a measure of non-compactness because this phi is not algebraic, subadditive, and not regular. So therefore, second is not a measure of non-compactness. First, one example of measure of non-compactness. By using these two measure of non-compactness, Darboux and Sadowski, they have given some fixed point theorems. And Darboux theorem is saying that if X is a Banach space and M is a subset of X, which is a non-empty closed convex and moderate subset, and T is a mapping from M to M, which satisfies this condition: alpha T u is less than or equal to K into alpha u, where K is strictly less than 1, then T has a one fixed point. So this is the Darboux fixed point theorem. And next one is here by given by Sadowski. In the next one, the K is equal to 1. So first is called K set contractive condition, but second there is no any K. K is here 1, so it is called only condensing mapping. T is K set contractive and T is here M condensing. So these two are the fixed point theorem given by Darboux and Sadowski. Here, the beauty of these two theorems are that these two theorems involve the can be used for the operator which are not compact. The previous theorems, order theorems, was using the compactness of the operator, but these are not requiring the compactness. So using the measure of non-compactness type of operator for operator, we can also discuss the some existence of the fixed points. This example is showing that whenever k equal to 1, we take in the this Darboux fixed point theorem, then we will not get the fixed point of the operator t. Here we are getting in the last line, we are getting k equal to 1. So this k equal to 1, t is satisfying the condition for k equal to 1, but the mapping has no any fixed point. So whenever k equal to 1, then the Sadowski theorem gives the existence of the fixed point. There are some mathematical problems which involve two operator a and b in this combination: ax equal to bx equal to x, ax plus bx equal to x. So for this type of models 31, there is one famous theorem by given by Kolmogorov. So existence of the fixed point is also guaranteed if the mapping A and B satisfies these three conditions. On a subset C which is a convex closed say subset of a Banach space X, and if A and B are the two mapping from C to X satisfying that A is a contraction mapping and B is a compact operator, then AX plus BV which belong into third is also needed, is 3, then A plus B has at least one fixed point. So this combination of the two operator is has a fixed point. This is given first time by the Karnofsky. This is also famous theorem, Karnofsky fixed point theorem. Here, this uh, Burton has defined the large contraction, and then Predesky has defined the generalized contraction. These two contractions are also involving some type of functions. Generalized contraction is involving one function gamma, and if it satisfy the d of tv, if it first this t is said to be generalized contraction if there is exist a function gamma which satisfies these conditions, then generalized contraction was introduced. Kelly and Samet has also used some type of contractive define some contractive conditions by involving some this type of function control functions. Then later on, Chow has introduced this function theta, and using this function zeta, he defined the L contraction, and uh, he also proved that on a complete metric space, every L contraction has a unique fixed point. Then, using the measure of non-compactness, L alpha contraction was also introduced by Jade et al. And they have also this condition last in this theorem. The last condition is here involving theta, theta and alpha. These three control functions. Actually, alpha is the measure of non-compactness, and zeta and theta are the two functions. Then in one of our article, we have done one comparative study on this Banach contraction, large contraction, generalized contraction, and L contraction, and we have given some example that uh, generalized contraction, a mapping T, if suppose it is a L contraction, then it need not be a generalized contraction. So this is one example where we are showing that T is not satisfying the generalized contractive condition requirement, and on the other hand, this T is satisfying the our L contraction. So, so L contraction need not be a generalized contraction. Picture is saying that every Banach contraction is a large contraction is generalized contraction is contraction, but L contraction need not be generalized. Converse, reverse implication need not be whole. This example is related to that. This is not L contraction, but not generalized contraction. And in our paper we have proved that every L contraction T on a metric space XD is alpha condensing, and we also proved some Korenoslawski fixed point theorems by improving the condition number 1 and third. Condition number 1, we are using L contraction instead of the contraction, ordinary contraction, and number 3, we are replacing that belongingness condition by this containment condition. So this is one improved version of the results which is given by Korenoslawski. These two corollaries are here showing that our result is the generalizing the previous results. The second corollary is showing that it is the our result is improving the Karnofsky fixed point theorem, and first it is also improving the theta contraction. Uh, Here some concepts of the fractional differential equation I am here listing. We all know that the gamma function, which is the generalization of the factorial function. Similarly, here gamma k function, the gamma k function is here generalization of the gamma function, and this gamma k function is here defined by this integration 0 to infinity s power z minus 1 e to the power minus s power k upon k ds. And this k gamma function has the satisfying this three properties 1, 2, and 3. And considering this gamma k function and this weighted space, I am coming quickly to the uh, this integral equations. The integral equation which is defined by the Kuhn in his paper 40, uh, k psi Riemann value integral equation of integral of order mu. So which is a one integral equation number 34, k psi Riemann value integral equation of order mu. And the next 35, this is the definition of the k psi Hilfer fractional derivative of a function h of order mu, and the type nu, which is between 0 and 1. So number 34 and 35, then the k psi fractional derivative can be presented through a k psi Riemann value fractional derivative by this number 36. So there are many definitions related to the fractional order derivative and integral. So here just I am listing few of the important definitions, and we will discuss we can discuss one existence result for the one initial value problem in our one of the paper. We have discussed the existence result for this initial value problem. The problem number 37 is one initial value problem related to k psi Hilbert fractional differential equation. And this lemma, in this lemma we are converting our that given this lemma is here actually. If you observe the problem 37, the right hand side, then it is involving a function f, which is a one three variable function, capital F, in the 37. That function f, we are instead of taking this case, first we are dealing the right hand side for a single variable case in the number 38. So this lemma is here showing that we can write the equivalent form of this initial value problem, which is in 38, to its a one equivalent integral equation, which is here in last line. The last equation is one integral equation in for this 38 equivalent integral equation. And this lemma is again uh, giving the integral equation of the our original problem k psi Hilbert fractional differential equation 37. The lemma number this number 40 is the 39, and in this lemma we are writing the equivalent integration of the our given problem. And here in this theorem we are showing one existence of the solution of the k psi Hilbert fractional differential equation if the function satisfy, if the actually that function capital F satisfy these two hypotheses h1 and h2. H2 is just a one Lipschitz type of condition, and if it satisfies this h1 and h2, then it has a one unique solution. This initial value problem has a one unique solution, and that problem we tried to explain by one circuit equation. The circuit equation, I hope we are familiar about the Ohm's law and Kirchhoff's law. Kirchhoff's law is saying that the sum of the voltage drop around any closed loop in a circuit is equal to 0 in presence of one external force. If the equation number 42 is here saying that Kirchhoff law, Rj plus 1 by C QC equal to external force. And this 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 second equation, which is one differential equation, R into dq by dt plus 1 by C Q T equal to epsilon T. This is the circuit equation for this Kirchhoff law. And this circuit equation first we are writing in terms of the fractional k psi Hilbert fractional form, which is here given by this equation. The circuit equation, same circuit equation, we can write in form of one k psi Hilbert fractional form. This circuit equation, this is our circuit. Uh, uh, First, in the circuit we are not uh, there is no any flow of any current. The external source is not connected. So we in the figure P, the external source is connected. Then the charge is flowing from minus to plus in the external force, and in that is the capacitor. In the capacitor, the charge is flowing from plus to minus. And whenever we disconnect the circuit, that means the switch is connected to now the point B in the figure number C, third figure. Then our capacitor is working and charges is flowing from minus to plus, and then the loop the circuit become closed. And whenever there is no any external force, then that means the right hand side of this circuit equation ET, that is here equal to 0, and in that case our given equation initial value problem become a problem like 44. This is one example. 44 is one example of that equation, and this for this case we can discuss the hypothesis H1 and H2 is satisfied by this involved mapping F here, because this quantity is strictly coming less than 1, and therefore the problem has a unique solution, and this is the solution. We have also calculated the solution, and solution is given by this Qt, which is in fractional form. Now we have also analyzed for some different functions and for different orders. In every case, this is here satisfying. So finally, what we are trying to say, we can use the so many control functions to make our circuit model in such a way that it will perform with more efficiency. Uh, that can be possible by considering the fractional model. Yeah, some related figures. Coming to the development on the fixed point results, further improvements are there by considering various generalized form of the metric spaces. In the Banach space, we can have some fixed point theorems. In the Hilbert space, also we can have some fixed point theorem, probabilistic metric space. There are many generalized form of the metric spaces in the literature. These are the some of them. These are there is a many, huge list of the generalized form of the metric spaces, and the respective fixed point theorems are also proved in these spaces. However, some in these articles, some authors have shown that the fixed point results which are proved in the generalized these spaces are trivial, because they can be obtained directly obtained from the standard metric spaces. So these are some related papers, nice paper in the literature. Then next direction, how to extend the Banach contractive mapping to the multi-value mappings. And there are huge literature on the multi-value fixed point theorems in the literature. We can also improve, and by showing that the existence of the coincidence point, common fixed points means fixed point for more than two or more than three mappings for the nonlinear mappings. They require various concepts. There are various type of mapping: commuting mapping, weakly commuting mapping, compatible mapping, weakly compatible. That is related to the common fixed point literature. So that literature is started from 1976. So there is a large number of research article on this particular area. Number 5. Next, how we can show the existence of the coupled fixed point theorem, coupled fixed point, triple fixed point, and other this type of fixed point. So there is a separate literature on this direction. How to extend the concept of fixed point to the best proximity points. So whatever here I have discussed, that is related to the fixed point. Best proximity point is the point whenever the mapping has no any fixed point, then we think about the nearest point which satisfy the our requirement. So that is related to the best proximity point theory. So this direction has a large number of uh, research in this best proximity point. Also common best proximity points. How to extend the Picard iterative sequence. The Picard iteration is here used in all the previous discussion. Picard iteration can be further improved by this type of iteration: Man iteration, Isoka iteration. There are some famous iterations that are also improving the Picard iterations, and using that we can say about the convergence is better than Picard iterations. Then we can also discuss about the applicability of the Banach fixed point theorem and other fixed point results to the applied science and mathematics. Applications like in these areas for nonlinear differential and integral equation, metric equation, stability of functional equations, fractional calculus, or homotopy theory. These are some area where we can apply. And not only this, we can apply the Banach fixed point theorem or any other fixed point theorem in all these areas. Discussing the existence and uniqueness of the ordinary differential equation, Volterra integral, full freedom integral. We can also apply the fixed point theory in the optimizations, in learning theory, stability theory, various functional equations, and matrix equation. And fractional differential equations. So these are the some areas application point of view. Here I have tried to summarize the huge area of the fixed point theory by showing some of the famous results in the literature. The theory is a very huge and application point of view. Has a very nice application in every branch of science and engineering. Okay, thank you for thank you for thank you for giving this inviting me for this 2 day program, international conference on this computer and mathematical sciences. And thanks.
Thank you, sir. Thank you for sharing your knowledge on this important topic and your views with the participant. Now I call upon Honorable Rupari Kale Madam for her remarks.
So much, sir. It's really very wonderful
Yes,
session.
yes.
Actually, I'm not so much aware about the maths because I'm computer science teacher, but it was interesting. Thank you so much, sir.
Okay, thank you, thank you.
Thank you very much, ma'am. I'm thankful to Honorable Rupali Kale Madam and our invited speaker, Honorable Dr. Deepesh Kumar sir, for their valuable guidance. Thank you once again. And with the permission of the chairperson, I declare that the session is over. Thank you, sir. The sixth session will commence immediately after it, and I hand over my.
Hello. Good afternoon. A very good afternoon to one and all. We are heading towards technical session 6, which is invited talk of an international conference on next generation innovation in computer science, AI, and mathematical science. We are honored to have Dr. Sanjay Boyer sir from Department of Mathematics, Pulsing Naik Mahavidyalaya, Pusat, as a chairperson for this session. May I now request Dr. Revaskar sir to please felicitate him by offering bouquet and memento. Thank you, sir. May I now request Dr. Suradkar sir to felicitate Ashwini Randare madam. Thank you, sir. Now I take this opportunity to introduce our chairperson. He has currently working as a vice principal of Fulsing Naik Mahavidyalaya Pusat. He has a vast 12 years of teaching experience. His administrative experience include as a vice principal, officiating principal, dean academics, IQAC and NAC coordinator, HOD, head department of mathematics. He has published 57 papers in international peer-reviewed journals, 25 in conference proceedings, 24 papers are published in UGC care listed journals. Q1 and Q4 ranked 16 papers are published, and he has 10 research paper published in journals which have impact factor between 1 to 10. And he has a recognized supervisor of Sant Gadge Baba Amravati University Amravati and JJT University Junjunu Rajasthan. He has under his guidance 4 students are awarded PhD and 6 students are awarded PhD degree and 4 students are working, and he has PhD reviewer and journal reviewer also of SRTM University Nanded, BMU University Sambhajinagar, JJT University Rajasthan, and journal reviewer for International Journal of Theoretical Physics Review article, Chinese Journal of Physics, Journal of Mathematical Physics, Indian Journal of Physics, and he has patents to his credit. India 12 patents in Indian design patents, 2 in Australian innovation, 1 in German utility, 1 in United Kingdom design, 3 patents are filed in design patents, and 40 books are published, which is added in NEP curriculum of SGBAU Amravati University Amravati. His awards and achievements include a member of Board of Studies in Mathematics of SGBAU Amravati. He has a resource person for NEP School Connect 2.0 program by SGBAU. He is recipient of Award of Excellency by Gyanpit Publication Amravati. He is a recipient of Outstanding Scientist Award by VD Good Professional Association India, recipient of Young Researcher Award by Institute of Scholars. His academic achievements and recognitions are Swayam NPTEL Coordinator, ASHE Coordinator, NEP 2020 Coordinator, Research Advisory Committee Coordinator, Taluka President of NUTA, Student Development Officer, SGBAU Student Development Section, Amravati. And he has worked as a NAC and IQAC coordinator also. Sir, welcome you. It is also privilege for us that we have Dr. R. Vijay Kumar from Department of Mathematics, Annamalai University, Tamil Nadu, as an invited speaker for this session, a very versatile and learned personality who will join us in online mode. I welcome you, sir. Let me introduce our guest. Dr. R. Vijay Kumar sir is an assistant professor of mathematics at Annamalai University, Tamil Nadu, and is presently on deputation to Periyar Government Arts College, Kudaluru in Tamil Nadu. Dr. R. Vijay Kumar obtained his PhD degree in mathematics in area of applied mathematics from Annamalai University. He also did his bachelor and master degree in mathematics from Bharatidasan University, Tamil Nadu. His research interests are fluid dynamics, porous media, magnet hydrodynamics, heat and mass transfer, computational fluid dynamics, mathematical biology, differential equation, and numerical methods. He has published 50 research papers in various national, international journals and conferences. He guided 3 PhD students, and presently 4 students are doing their PhD work under his supervision. In addition to teaching and research, he is and actively involved in various administrative responsibilities to organize conferences and workshops. He visited the Eastern University in Sri Lanka and University of Tun Hussein on Malaysia. Dr. Vijay Kumar delivered many guest lectures and invited talks in national and international conferences, workshops, and seminars. Dr. Vijay Kumar sir is a life member of Indian Mathematical Society. He is a reviewer for many reputed journals and authored one book. I welcome you, sir, on behalf of organizing committee of this conference. May I,
Thank you, ma'am.
may I now request Dr. Vijay Kumar sir to share their valuable insight on mathematical modeling of biological fluid flows. Over to you, sir.
Thank you for your brief introduction, ma'am. Shall I share my PPT, ma'am? Shall I start the session?
Yes, sir. Yes, sir. Just a minute.
Yes.
Hello, sir.
My
Your
screen is
PPT
visible.
is shared.
My screen is visible or not, ma'am?
Yes, yes, visible, sir.
I
Start.
shared my PPT is visible. My PPT is visible or not, ma'am?
Yes, sir. Your PPT is visible. Start your session, sir.
Okay. It is visible.
Yes, sir.
Okay. So let's go for sections.
On your slideshow, sir.
Uh,
Sir, present your PPT in slideshow mode, please.
yeah, I choose only in slideshow mode only, sir.
Actually,
So
it
in
is a
my screen
partially
is shown,
visible.
sir. I share entire screen, sir. I shared the PPT entire screen only, sir.
Okay, sir, no problem at all. You can continue.
Here I shared my PPT entire screen and it is
Okay, sir.
okay. So my title is a mathematical modeling of biological fluid. So the topic of the outlines of my presentation is the introductions. So in introductions, it's cover what is a mathematical modeling, what is the fluid dynamics, and what is the applications or my work is going. That is the next for mathematical formulations, method of solutions, results and derivation and conclusions. And some reference are given here. Um, so next, so modeling, mathematical modeling. So what is a mathematical modeling? What is a mathematical modeling? So why it is necessary and what is the uses and what are the types and what the process and what is the main dimension analysis. So for first, we see what is a mathematical modeling. So it is a representation of real world problems in mathematical form, which is some simplified assumptions which helps to understand in the fundamental and the quantitative ways. So it is a complement to theory and the experimental, often to integrate them. So here's a widespread applications, the branching of science, engineering and technology, biology, medicines, and some other interdisciplinary areas. So next, why it is necessary? So to perform experiments and solve real-world problems may be risky and expensive to time consuming, and also improve the quality of work and reduce the changes, errors, and the rework. However, it is only the complement does not the theory and the experimental in the scientific research. Next, what is the uses? So, sorry, what is the uses? So, uses of some modeling research solves the real world problems and has become a widespread due to the increasing computational power and the computation methods. So, some areas where the mathematical models highly used. So, that is a climate modeling, aerospace, some manufacturing, designs,
Sir,
environment
hello.
economics, material
Hello, sir. Sorry for
research.
interruption. But you have slideshow is not going on, sir. Only slides are showing.
Yeah, I'm not just I'm telling I'm not brief introductions. I'm not showing here.
Okay, okay, sir. Thank you. No problem.
Okay. So some medical and biology, etc. So next is the types. What are the types? Means here there is a two. Here describes the two types. One is the empirical models and another one is a theoretical model. So empirical model is the experimentals and the observations one, and theoretical model describes the statistical and the mathematical and the computationals. So finally, one is a dimensionals. So dimensionals is based on the physical law. That is before going to the some uh, mathematical model. So you have to balance. You have to balance the equations. Okay, the equations are same units. So next, some modeling from others. So the mathematical modeling, it is a applied mathematics at work, MS Kalin. So applied mathematics, it is a consist of applying mathematics to real world problems, so JLSIM, and applying it is a concern with a better understanding of phenomena by the use of mathematical methods. The process of formulating the mathematical model is often called a mathematical F1. So these are here the modeling is one of the, it is a teamwork. So it is not a single discipline. We cannot do this one. So the teamwork means such as computer science, mathematics, science. So computer science helps to plot the graph. For mathematics, we have solved the problem. So science, we can go for the biological field means we have to take real problems. So the combination of these three, those things only, we can go for mathematical modeling. So this is various constraints on our arterial flow analysis. So this one's this one's helpful to design the physical configuration, such as geometric representation. It only helps. So before going this one, we have to know the basic properties, fluid properties of fluid flow properties. We have to know. Okay, the arterial blood flow analysis means. So this one is the blood vessels. How the vessels should be means. The vessels should be wall length, geometric, and cross sections. So wall means it is a elastic, viscoelasticity and elastic means that is a realistical displacement or longitudinal length. So how we can take the length, whether it is the length we can take long way or short way. So what is the geometric means? It is the vessels is a straight or branching or curved like that. You have to take it up. Next one is the cross section. How we can take the cross sections means the constant circular or taper. Taper means it is narrow like that. So next one is the blood. So the blood type. What is the rheologically means the blood that is a classified described as a Newtonian as a non-Newtonian. Newtonian or non-Newtonian. Newtonian, what do you mean by Newtonian means the example for Newtonian is water. And non-Newtonian is blood. Blood is one of the good example for the non-Newtonian. So Newtonian, what do you mean by Newtonian means it does not obey the Newton's law of viscosity. No, sorry. It obey the Newton's law of viscosity. What do you mean by Newton's law of viscosity means the rate of shear stress is directly proportional to the rate of shear strain. So non-Newtonian means it does not obey the Newton's law of viscosity. So time-wise, I want to consider the zones whether the flow is a steady state or the flow is a wavy form like that, pulsatile. The flow patterns, whether the flow is a laminar or turbulent. So laminar means it is a well-defined path. The one layer is it is a well-defined path. Turbulent means it is a zigzag in motion. So main flow is a state, whether the flow is a straight or bifurcation, look like a tree. Next one is the compressible. Compressibility means so we have to choose before the physical configurations. We have to assumption for all those things. So compressibility means here we consider the density is constant. It means it is a compressible. So density is not a constant. There is a no incompressible. Okay. So next one is how we can choose a vessel's bed. It is a rigid or elastic deformation. Elastic deformations, there is a circular motion, so that is a radially or longitudinally. So next one, this is a process. So I mean the process. So process means first we choose a real world problem and simplify into the working model and represent into the mathematical model and translate into the computational and simulate to the results and discussions or the conclusions and interpret with the real world problem. So this our research is not related with the relate with our real world problem. Means we go for changes in the assumptions. So this is the flowchart is given here. There is a start, formulation. There is a problem, mathematical parameters. So after by using the parameters only, we can plot the graph. So solutions. So solutions, there is a two cases. One is analytical or computation, numerical methods and evaluations. Whether it is satisfied means we go again, and otherwise it should stop. So this one is the introductions. So here the biological fluid. So in the biological fluid means in our human body, the biological fluid is a mucus. Mucus is one of the fluid, and the synovial fluid. Synovial fluid is a so there is a joint. The joint in between the joint. That one is the synovial fluid, plasma, blood. The major, the primary fluid in our body is blood. So it is created out of during the last decades. Many researchers have done in the fluid dynamics of the biological fluid with the impact of magnetic field. So in the artificial organs, when during the fixing of artificial organs, there is a blood damage. So blood. So what is the cause? The blood damage means it is a so blood damage. So it is a loss of blood. A hemoglobin is a loss. That one is that is known as a hemolysis. That is a artificial organs implanted causes various form of blood damage due to the lack of biocompatibility of surface. The surface produces stress leading to the forces. These forces damage the RBC and hemoglobin to lose known as hemolysis. So here this is the diagram. So this is a normal RBC. So during the artificial organ fixing time, the normal erythrocytes, RBC is nothing but the erythrocytes. It should be changed into like this spirocyte. There is a spear-shaped erythrocytes. After this, the rupture of RBC, which is subsequently it should be released from the hemoglobin into the blood. So it is a very weak. So that is we get the nutrition. It is a deficiency of nutrition. So this model the same already. This work is done by Professor Rudraya and okay. So next in this model, I choose a non-metallic fluid is a coupled stress fluid, magnetic field. Magnetic field. So I go for okay. Magnetic field applied the vertical of the flow direction. This is our geometric representation. So horizontal is the x-axis, vertical is the y-axis. So here the in the horizontal, I apply the magnetic field. That is a B naught is a magnetic induction. So apply the vertical of the flow directions. So here I consider is a steady means is a time independent. Laminar means the flow is a well-defined path. Fully developed means unidirectional. Here I just consider the unidirectional. So suppose if you want to do two-dimensional means you go for numerical methods. Here I am using only a unidirectional. So that is a velocity along x directions only. So uniform magnetic field is applied the vertical of the flow directions. This is my assumptions. So my aim is to find the dispersion of solute. Here solute is nothing but a nutrition. So this is the basic equations of fluid flow. So basic equations of fluid flow means that is the governing equations. The governing equations contains 1, 2 is the Navier-Stokes equations, 3 is the conservation equations. So here the conservations of mass is incompressible fluid. So incompressible fluid is nothing but a density is constant. Okay. So this one's what is the equations? One is a conservation of mass is the amount of fluid entering into the volume is equal to the amount of fluid leaving from that volume in the absence of source and sink. So this one is the conservation of momentum is a force equal to mass into accelerations. That is a Newton's second law. So rho in equation 2, rho is the density mass. So this one is the acceleration, and right hand side is the forces. These are all forces in equation 2. So that is this rho. So this one is a momentum equation in the vector form. So first term is for steady state. So this one is a viscous term, and right hand side is the force. The force can be described into internal force and the external force. So internal force in our blood, it contains a shear stress. Shear stress means the layer between the, so it is interact with the layer. That is this one viscous term, the second term. And the next one is a minus grade P is a pressure. It is a normal stress. That is the force is normal to the flow direction minus gradient P. Okay, so this is a minus lambda gradient for Q vector is this is for non-Newtonian fluid. For that purpose, here I am considering the fluid, the flow is a non-Newtonian fluid. So majorly the blood flow is a non-Newtonian fluid. The right hand side is a magnetic effect minus J cross B is a for the impact of magnetic field. The conservation of species is a it is denote the it describes from the difference due to the concentration gradient. So this is our major equations and the corresponding boundary conditions. So our choice, what is the boundary conditions are here using means the boundary conditions on the velocity. The rigid boundaries means the velocity at the wall is it is vanishes at the boundary. So there is no in the boundary there is no velocity. The free surface means it is dependent on whether they consider the surface tension or not. So next one is the Bevier-Joseph conditions. This is a 1967. So this one equation is for the slip condition. Whether if you use the slip condition means we can use this boundary condition. There is a slip condition means at the wall there is some velocity. So this one boundary conditions on concentration means the total rejected solutions wall impermeable boundary conditions. So as you see the gradient with respect to x, the gradient concentration gradient is also 0. So at wall there is a chemical reaction is occur means we can use the heterogeneous chemical reaction, this one. So these are the boundary conditions. So used we can apply this model. So here unidirectional means this right hand side left there is a second in the equation 2. The left hand side it will be skipped. Unidirectional means. So in the right hand side the pressure gradient. This one is a viscous term. Second one and next one is a next one is a coupled stress fluid. Next one is a magnetic field. So equation 4 there is a this one is a one dimensional. Next to equation 6 is the concentration equations. So next to the corresponding boundary conditions I applied for the above equations. Equation 9 is I consider this one is a no slip condition. So no slip condition means the velocity at constant at the ball is a constant. For vanishing the coupled stress, so I'm using the equation 10. So remaining 10A to 10E is concentration equations. So here I'm introducing the already we discussed about the dimensional parameters, dimensional. So I'm introducing the dimensional this term in the equation in the momentum equations and the concentration equations. We get the equation number 11 and 12. So after applying the dimensionals, we get the parameter. A is a coupled stress parameter, M is a Hartmann number, and the P is a constant pressure gradient. So here in concentrations, we get the only the Pictet number. Okay, so here the corresponding, so after introducing the dimensions parameter in the boundary conditions, we get the dimensionless boundary condition unit, sorry, equation 13 to 14. So after simplifying, this one is a second order, the equation 11 is a second order differential equation with the constant coefficients. We can use directly, we can simplify, we get the velocity equation number 15. So this one is the axial normalized axial component velocity is equation 16, and average velocity is a u bar is equal to 1 by 2 this one. And the next, so next we have to calculate to find to study the dispersion of solute with and without porous medium. So what do you mean by porous medium? It is an interconnected voice. So here dispersion of solute, there is a we can simplify the equation 12 by using this model. There is a analytical means we go for Taylor's and the Airy's dispersion model, and this model valid for large time. But after injecting a solid into the medium, but in generalized dispersion, here I am using only the generalized dispersions. This one is a valid for all the times. So there is another method is also Mitchell approach, random walk approach, Smith delay diffusions. And if you go for numerical method, means there is a finite difference, finite volume method, finite element method, spectral method, and Barton-Stokes approach, Smith approach, integral transform approach. These are to find the to calculate the concentration equations. So here I go for a generalized dispersion by using this procedure of Gill and Shankar Subramanian 1970. So these are the methods I used. So equation 30 is to find K2 is a dispersion of soluto, and theta m. That is from equation 38, find the dispersion of soluto, and 32 is to find the mean concentration. So here I plotted this graph by using the Mathematica software. So if you want to go for MATLAB, so there is a many software is available. So here in our university we use Mathematica and MATLAB only. So here just I want to discuss a few graphs. So here this is a unidirectional. So the velocity is as it is in the parabolic in motion. If the Hartmann number, if you increase the Hartmann number, the velocity is decreases. That is it is a finally it should be in the plug flow. The plug flow means it is a straight line like this. Okay. So next one is next parameter is a couple stress parameter. This one is it is also in the parabolic in shape. If you increases couple stress parameter, it should be it is also in parabolic in motion. So next one is this is the main thing is dispersions. How the dispersions? If you increase, I give the parameter value is 0.5, 1.5. It should be if you increases the Hartmann number, the dispersion is reduces. So this one is obviously true because if you the rapture of RBC, so definitely the nutrition transport is it should be reduced. So next one is this one is also couple stress parameter. If you increase the couple stress parameters of 5, 20 means that should also decreases, but it should be converged nearly the point 3. It should be converged. After if you are extending up to infinity means it should be converged. So the result is useful to design the artificial organ free from the side effect of hemolysis. So this one is the mean concentration. It is look like a bell shape. It is symmetric in manner. If you increase this Hartmann number, so the mean concentration is increases. Then the results also, if you increases couple stress parameter, it is also increases. So the results are very useful, and these results are very useful in designing the artificial organs, and proper way the device material should choose and minimize the hemolysis caused by the artificial organs. So these are the appendix. So if you go for software means, so there is so many softwares are using, but in our university the star CD only using in our mechanical department. So these are the main thing is a fluent ANSYS and ANSYS star CD. Some console like that we are using. So this one is a major thing I used the reference from the Gill and Sandra Subramanian and Professor Rudraya. Rudraya, Dulal Paul, this Zigzalaki, the basic concept about the biological fluid, and the professor, my guide, Professor Nirmala Chakar, so they also guiding like in the biological fluid. Okay, that's all. The presentation is over.
Hello.
Yeah, audible.
Hello. Finished, sir? Hello.
Yeah, I am
Okay.
finished now.
Okay, sir. Thank you, sir. May I now request Chairperson Dr. Boyer, sir, to give his remark on this talk.
Hello, sir.
Hello, sir.
Stop your sharing.
Hello, sir.
Hello.
Hello, sir. May I audible, sir?
Stop sharing.
Okay, sir. Okay.
Session is open for any question from audience. Okay. In the conclusion, that today's invited talk delivered by Professor Dr. R. Vijay Kumar has been highly informative and intellectually enriching, sir.
Thank
The
you, sir.
speaker has
Thank you, sir.
presented the topic with the great clarity, depth, and insight, offering valuable perspectives that will certainly benefit researchers, teachers, and students alike. The session successfully stimulated meaningful discussion and reflection, highlighting the current trends and the future directions in the biological field. On the behalf of the organizing committee, I sincerely thanks to the esteemed speaker, Professor Dr. R. Vijay Kumar, for sharing their expertise and participants for their active involvements. This session has significantly contributed to the academic success of the conference. Thanks for giving the opportunity to chair the session, which was nicely represented by Professor Dr. R. Vijay Kumar. I sincerely thanks to Dr. R. Vijay Kumar for accepting our invitation. So on the behalf of this organizing committee, once again, I thankful to the very much, sir, and thanks for your nice presentation. Thank you very much.
Thank you. Thank you, sir. Thank you for giving this opportunity, sir.
As we approach to the
Shall I-
conclusion, we extend our deepest gratitude to Chairperson Dr. Boyer sir for chairing the session, Speaker Dr. R. Vijay Kumar sir for accepting our request and sharing his insightful thoughts. I am also thankful to all dignitaries present over here, joined us in online mode. Thank you everyone. With the permission of Chairperson, I declare this session is over. Thank you once again very much. Now we will soon meet for valedictory session in this hall. Thank you everyone.
Hello, hello, good afternoon. Swagatam, Suswagatam, Shubhaswagatam. A very warm welcome to all the dignitaries, researchers, and participants. As the final chapter of this conference unfolds, we are here for the valedictory function of two-day international conference in on next generation innovations in computer science, AI, and mathematical sciences, organized by the Department of Computer Science and Mathematics of Shankarlal Khandelwal College, Akola, sponsored by Pradhan Mantri Uchchatar Shiksha Abhiyan. In an era where algorithms influence decisions, artificial intelligence reshapes cognition, and mathematical sciences provide the language of the universe, this conference stood as the beacon of interdisciplinary synergy. We are delighted to have the president of our Shikshan Prasarak Mandal, Shiksh- Akola, Honorable Dr. Taratai Hatwalne, as the president of this valedictory function. We are elated to have Honorable Dr. Avinash Kadam, Sir, Associate Professor and Head, Department of Computer Science, Shri Shivaji College, Chikli, Buldhana. Accompanying them on the dais are our college principal, Honorable Dr. Sabu Sir, convener of the conference, Dr. Dipti Petkar, organizing secretary, Mr. Ravindra Revaskar, and treasurer, Dr. Nitin Suradkar. Astronomer and scientist Carl Sagan beautifully reminds us that somewhere something incredible is waiting to be known, a thought that truly captures the spirit of this conference. Today we celebrate not only academic achievement but also shared courage to question, to explore, and to innovate. Now let's proceed towards felicitation. I request Honorable Dr. Sabu sir to kindly welcome Honorable Dr. Taratai Hatwarne. Thank you, sir. I would like to take this opportunity to introduce our chief guest, Honorable Dr. Avinash Kadam sir. Respected sir completed his bachelor's degree, master's degree, and PhD from Dr. Baba Saheb Ambedkar Marathwada University, Aurangabad, under the valuable guidance of Honorable Dr. K.V. Kale, Vice Chancellor of Marathwada University. Currently, he is serving as an associate professor and head of Computer Science Department at Sri Shivaji College, Chikli. Respected Sir is the head of research center at his college, and along with that, he is also a member of Board of Studies in Computer Science of Santa Gadge Baba Amravati University, Amravati from 2022. Sir has two national patents published in his name on automatic detection of genetic diseases in pediatric age using pupillometry and advanced secured ATM system with fingerprint, keypad, and voice-enabled three-layer security protection. He is the recipient of first prize in poster presentation at state level Avishkar in 2008 and also the recipient of University Golden Jubilee Research Fellowship in 2008-2009 bestowed by Dr. Baba Saheb Ambedkar Marathwada University Aurangabad. Along with that, he is also a member of editorial board. Sir has published over 26 research papers in various national and international journals, has edited two books, one journal, and along with that has 10 book chapters. With an extensive teaching experience of over 13 years and research experience of over 19 years, he is also a recognized PhD supervisor with 4 students pursuing research under his guidance. We are elated to have such distinguished personality amongst us today. I request Honorable Dr. Tarati Hatwane to kindly welcome and felicitate Dr. Avinash Kadam sir. Thank you, Taratai. I also welcome our principal, Honorable Dr. Sabu sir, and everyone present on the dais. I would now like to invite Dr. Nitin Suradkar to present the report of this conference.
Good afternoon to all. We have reached the last session of the session. Today's conference. Respected Chief Guest, Honorable President, respected Principal Sir, and organizing committee members on the dais, invited speaker, chairperson, faculty members, researchers, participants, and my dear friends. Good afternoon to everyone. It is my pleasure to present a brief and heartfelt report of International Conference on Next Generation Innovations in Computer Science, AI, and Mathematical Sciences, organized by Department of Computer Science and Mathematics during 21st and 22nd January 2026. The response to this conference was truly encouraging. We had 119 registration with participants including faculty members, research scholars, students, professionals from different institutions. The conference began on 21st January with grateful inaugural ceremony. We were honored by the presence of Dr. Milinda Barhate, Honorable Vice Chancellor, Santa Gadage Baba, Amravati University, as an inaugural guest. The welcome address by our respected principal, Dr. James Sabu sir, followed by insightful words from Dr. Vidya Sharma ma'am and Honorable Shri Gopalji Khandelwal, who motivated everyone present in the session. The keynote address by Dr. Milind Kumar Sarode was both inspiring and informative. The academic journey of conference continued with the series of technical session. In the technical section first, featured by Mr. Jingcheng Zhu, a machine learning engineer developer from Melbourne, Australia. He shared global perspectives and recent developments in machine learning. The session was smoothly chaired by Dr. Arvind Tade sir. The second technical session, Mr. Ashish Manchanda, data scientist from Coles, Australia, spoke about the practical applications of data science in real world scenarios. This session was effectively chaired by Dr. L.R. Mule sir. Later in the day, the technical session third was dedicated to paper presentations. Researchers, students present their work in the areas of artificial intelligence, computer science, and mathematical science. The session was guided by Dr. V.R. Patil sir and Dr. R.M. Dhaigude sir. The second day of the conference continued with the same enthusiasm. Technical session 4, the poster presentation provided a creative platform for participants to present their research visually. The session was evaluated by Dr. S.R. Bhoyer sir and Dr. A.N. Rangari ma'am. The technical session 5 featured an invited talk by Dr. Dipesh Kumar Patel sir from VNIT Nagpur. The session was chaired by Professor Rupali Kalel ma'am, Shivaji College, Akola. In the technical session 6, Dr. R. Vijay Kumar from Annamala University, Tamil Nadu, shared his insight on emerging trends in mathematical sciences. The session was chaired by the Dr. S.R. Bhoyer sir with Dr. A.N. Rangari ma'am. This today conference organized in the hybrid mode. The online streaming of all the technical sessions, including inauguration session and valedictory session, successfully handled by our technical team. The support of this particular team includes Professor Rohan Shirsat sir, Dr. Shekhar Dikshit sir, Viraj Bhagat, Sagar Vairale, and all. I am really thankful to them for their continuous support and effort. This is the brief summary of the today's conference. Thank you all.
Thank you, sir, for the brief report. Without any further ado, I would like to invite Honorable Dr. Avinash Kadam sir to kindly deliver the chief guest discourse and share his reflections on this conference.
Dignitaries on the dais, respected President Dr. Taratai Hatwalne, respected Principal Dr. Sabu sir, Convener Dr. Petkar Madam, Organizing Secretary, Revaskar Sir, Joint Secretary, Dr. Suradkar Sir, and PM Usha Coordinator, Dr. Thote Sir, and all organizing committee members of this conference, esteemed guests, invited speakers, and fellow delegates. Good afternoon to one and all today present here. Today I am very happy to present here as a rich and conclusion of this today intellectual journey. I feel deeply honored to stand before you to deliver the valedictory remarks for this international conference on next generation innovations in computer science, AI, and mathematical sciences. To the journey of innovation, these halls have been a melting pot of ideas. We begin with Dr. Milind Kumar Saroday's fascinating insight into transforming noisy images into masterpieces, and we traveled across borders digitally and intellectually with experts like Mr. Jing Cheng Zhu from Australia, who discussed the future of human robot collaboration in Industry 5.0, and Mr. Ashish Manachanda, who illuminated the world of context aware IoT. From the complex beauty of mathematical sciences presented by Dr. Deepesh Kumar Patel and Dr. R. Vijay Kumar to the vibrant energy of the poster and paper presentations. This conference has truly lived up to its next generation title. Today, I would like to share uh, one example of these issues that is related on AI. AI is a not only technology but is also new trending of financial market developed in the world. America and China is the biggest country invested more budget on AI related to basic facility and data centers and supercomputers development. But our country is less invested of this field. But the reality is that in America and in UK, the Indian scientists are actively worked as a team leader on this field. It's a big opportunities to all of us also. The 2017 year is the golden year. History will be written in golden letters of AI in the year due to the reason behind that the 8 scientists of Google written their research paper entitled with Attention is All You Need. The title is that Attention is All You Need. The main author of this paper is Mr. Ashish Vaswani. Depends on this paper, the chat GPT is developed. We know all this as per the chat GPT is very more useful and famous app we are already used. The man Ashish has not worked only for Google, it's also useful for the world. Mr. Ashish received Turing Award. It's likely to the uh, Nobel in IT sector. Many more Indian scientists work out like Ashish, such as Pushmit Kohli, Manish Gupta, Rohit Prasad, Arvind Srinivas, and many more. These are inspirable persons for all of us. An event of this magnitude does not happen by accident. It is the result of continuous planning, broad vision, and dedication. I express my deepest gratitude to this management of this institute uh, for providing the platform and support to host such a global event. Thank you, Dr. Sabu sir, for your leadership and fostering an environment where technology and academia meet seamlessly. And special thank to our national and international invited speakers. Uh, your expertise has bridged the gap between theoretical research and industrial applications. To the anchors, technical teams, and faculty members who worked behind the scenes. Your hard work is the reason we are concluding on a such high note. Finally, to the researchers and students, your questions, your posters, and your papers are the heartbeat of this conference. Finally, as we leave Akola to return our respective institutions, let us not leave these ideas behind. Let the next generation innovations we discussed here inspire your next project, your next equation, or your next line of code regarding related to our title, that is innovations in computer science and AI, as well as mathematical sciences. As it is said in the world of AI, the best way to predict the future is to invent it. Let us go for and invent a future that is smarter, faster, and more mathematically sound. Lastly, I formally declare this valedictory session is now concluded. Then, uh, turn to concluded. Then, I am stop here. G- Thank you once again, Dr. Principal, Dr. Sabu sir, for giving me the such opportunity as an chief guest of this valedictory function of this international conference. This today's conference is very much useful for new researchers or students and faculty members. Then, uh, as per this conference, today's benefits we are taken here, or we have uh, giving this expertise or experience or share with our students and our in next uh, challenge. Thank you once again, all of you. Thank you.
Thank you, sir, for such intriguing words. Academic gathering finds its true completion in the voices and reflections of its participants. For feedback, I would like to invite Shravani Rajvaidya.
First of all, thank you all of you for giving me this opportunity. Good afternoon to all present here, honorable dignitaries, respected guests, and lecturers, and all present over here. Myself, Shravani Anil Rajvaidya. I am a student of MSc Computer Science, second year, from Shankarlal Khandelwal Arts, Commerce and Science College, Akola. I sincerely thank the organizing committee for successfully conducting this international conference. I sincerely thank the organizing committee for successfully conducting this conference sponsored by PM Usha and organized by Department of Computer Science and Mathematics. The conference titled Next Generation Innovation in Computer Science, AI and Mathematical Sciences conducted in hybrid mode was very well organized. The research papers, representation, technical sessions and poster presentations were informative and well structured. The speakers from various colleges, universities shared their valuable knowledge and experiences, which greatly enhanced our learning. Overall, the conference was a valuable and enriching learning conference and experience. And I appreciate the efforts of organizers and volunteers for making these events successful. Thank you. Have a great day.
Thank you, Shravani. Now I would like to invite Nakul Nimje for his feedback.
Thank you, madam. for giving me opportunity to give some feedback about the international conference on next generation innovation in computer science, AI, and mathematical science. This conference is well organized, well structured, intellectually stimulating, and offered highly quality technical sessions covering emerging trending in computer science, AI, mathematical science. The interdisciplinary focus, expert keynotes, and interdisciplinary discussions made it valuable for academic and research scholars. It successfully facilitated interdisciplinary discussions by integrating mathematical foundation with advanced computational and AI-based approach. The quality of research presentation was commendable, with many papers addressing contemporary challenges, pro- proposing innovation solution. This conference serves as an effective platform for knowledge exchange and networking among the researchers. They appreciate the efforts of the organizer and the institute. Thank you.
Thank you. Next, I would like to call upon Swapna Rajankar for her feedback.
First of all, thank you, the organizers, for giving me opportunity to share my feedback here. Uh, Very good afternoon to all. Myself, Ms. Swapna Rajankar. I am a research scholar student from GS College, Khamgaon, and I am here to share my feedback. Okay, thank you, sir. The International Conference on Computer Science, Artificial Intelligence, and Mathematical Sciences was well organized and academically enriching. The hospitality and overall arrangement were excellent, ensuring a comfortable and productive environment for participants. The invited talks were highly informative and inspiring, providing a valuable insights into current research trends and future directions. Actually, I came here in this conference to present my research work and to discuss some innovative ideas with other researchers. But I enjoyed yesterday's technical session because the time limit was for only 3 minutes. In every conference, I used to face the time limit is up to 8 minutes or 5 minutes. But yesterday it was only 3 minutes. Within 3 minutes, you have to present your paper. It was really hard for us, but everyone has tried a best in that. And again, I am especially grateful to the principal, who is the chief organizer of this today's conference, Dr. J.M. Sabu sir, for providing an excellent international platform to present and interact with researchers from diverse fields. Uh, Convener Dr. D.H. Petkar ma'am, organizing secretary Professor R.P. Revaskar sir, and joint organizer secretary Dr. N.R. Suradkar sir, Professor R.K. Shirsat sir, and again Dr. Shekhar Dikshit sir, for their cooperative nature throughout this conference. I also extend my sincere thanks to the conference organizing committee for their dedicated efforts in making this conference a great success. Thank you. Thank you.
Thank you to all the participants for your valuable feedback. Your reflections will inspire us to further strengthen our such academic gatherings in the future. Along with stimulating talks and oration, a poster presentation competition was conducted as a part of this conference to provide a vibrant platform for researchers and students. Due to the remarkable quality and creativity reflected in numerous entries, the judges decided to add a consolation prize. The consolation prize of this poster presentation competition goes to Pranali Pimpalkar. The third prize goes to Rushikesh Sapkar. Second prize goes to Komal Gupta. And the first prize of poster presentation competition goes to Rahul Alone. Prizes of paper presentation competition are as follows. Third prize goes to Swapna Rajankar. The second prize goes to Arpit Raikwar. Moving forward, the first prize of paper presentation goes to Nikhil Mankar. Thank you to all the dignitaries. Congratulations to all the winners and participants. May this recognition encourage you to pursue your research and creativity with greater passion and purpose. I would now like to invite the president of this session, Honorable Dr. Taratay Hatwarne, to kindly deliver the presidential address.
आदरणीय मंच आणि उपस्थित श्रोतृवर्ग, आज मला पहिल्यांदा असं जाणवत आहे की अध्यक्ष म्हणजे खरंच खुर्चीची शोभाच असतो फक्त. काय चाललंय समोर, कसला विषय आहे काहीच कळत नाही. अक्षरशः आज माझी अशी अवस्था झाली आहे की हे AI म्हणजे काय प्रकरण आहे, मला काहीही कळलं नाही, काहीच नाही. आणि मग असं मनात येतं की उगीच आपण इतकी मोठी डिग्री घेतली, PhD पर्यंत काय शिकलो आपण काय माहिती. परंतु कॅटेगरी वेगळी आहे, हे सायन्स आहे सगळं. आणि सायन्स मधलं आर्ट्सच्या लोकांना काही कळतच नाही. त्यातले एक अपवाद मला असं वाटतं फक्त आपले प्रिन्सिपॉल साबू सर आहेत. बरोबर आहे ना? ते एकच असे अपवाद आहे बा, त्यांना सगळ्या याच्यातलं सगळंच समजतं. आणि त्याच्यामुळे मला नेहमीच त्यांचं कौतुक वाटतं की आर्ट्स ग्रॅज्युएट असून सुद्धा सायन्सचं सगळं कसं व्यवस्थितपणे सांभाळत असतात ते. छान वाटतं. आणि ह्या सायन्सच्या ज्या कॉन्फरन्स होतात ना, याच्यातलं खरंच मला काही कळत नाही. त्याच्यामुळे मी ह्या विषयावर काहीच बोलू शकणार नाहीये. परंतु ह्या ज्या वारंवार कॉन्फरन्सेस घेतल्या जातात, ह्यामुळे अनेक विद्यार्थ्यांना उत्साह मिळतो. नंतर त्यांना प्रोत्साहन मिळतं. त्या विषयामध्ये अधिक अभ्यास करावा, जास्तीत जास्त काहीतरी संशोधन करावं, अशी ऊर्जा त्यांच्यामध्ये निर्माण होते. हे सुद्धा खूप महत्वाचं आहे आणि त्यासाठी ह्या अशा कॉन्फरन्स होणं अत्यंत आवश्यक आहे. त्याच्यामुळे जे अशा कॉन्फरन्स वारंवार भरवतात आमच्या कॉलेजमधले लेक्चरर, प्रिन्सिपॉल सगळे, त्यांचं सगळ्यांचं मी अभिनंदन करते आणि मी इथेच थांबते.
Thank you, Tai, for your words of wisdom. I invite the convener of this conference, Dr. Deepti Petkar, to express gratitude towards the helping hands who contributed in the conduction of this conference.
respected President of the function, Honorable Dr. Taratai Hathwarne, Honorable Chief Guest Dr. Avinash Kadam Sir, Honorable Principal Dr. J.M. Sabu Sir, esteemed speakers, session chairperson, jury members, delegates, faculty members, research scholars, and online offline dear participants. As we arrive at the conclusion of this intellectually enriched 2 days international conference on next generation innovations in computer science, artificial intelligence, and mathematical sciences, CS/AI/MS 2026, held on 21st and 22nd January 2026. It is my proud privilege as the convener of this conference to propose the formal vote of thanks. On behalf of Shankarlal Khandelwal Art, Science and Commerce College, Akola, I extend my heartfelt gratitude to everyone who contributed to making this conference a grand success and truly global academic platform. First and foremost, we express our sincere gratitude to the Ministry of Education for the generous financial support provided under PM Usha Pradhan Mantri Uchchatar Shiksha Abhiyan scheme. This support form the cornerstone of our ability to organize an international conference of such high academic standards. We are deeply grateful to Honorable Taratai Hathwarne, President of Shikshan Prasarak Mandal Akola, for her visionary leadership and her inspiring presidential address during this valedictory session. Our sincere thanks goes to Dr. Avinash Kadam, Honorable Chief Guest, for this valuable discourse and insightful academic reflecting during the concluding ceremony. We also express our gratitude to Honorable Shri Gopalji Khandelwal, Secretary of Shikshan Prasarak Mandal Akola, for chairing the inaugural session. His encouragement and guidance is really inspiring always. We gratefully acknowledge Honorable Dr. Milind Bharate Sir, Vice Chancellor, Sant Gadge Baba, Amravati University, for gracing the conference as the inaugural guest, and Dr. Vidya Sharma Madam for her esteemed presence as the guest of honor on the first day of the conference. We owe a deep sense of gratitude to our keynote speakers, Dr. Milind Kumar Sarode, and our international experts, Mr. Jing Cheng Shu and Mr. Avinash Manchanda from Australia, for sharing their global perspectives. We also sincerely thank Dr. Dipesh Kumar Patel and Dr. R. Vijay Kumar for concluding enriching and insightful technical sessions, and all the honorable management members. My heartfelt thanks to our respected principal, Dr. J.M. Sabu, for his dynamic leadership, constant motivation, and unwavering support throughout the planning and execution of this conference. A special word of appreciation goes to Dr. Avinash Thote, PM Usha 3.0 coordinator, for his meticulous handling of the financial and administrative aspects of his prestigious grant. The success of CS/AI/MS 2026 is really truly a reflection of seamless teamwork and a shared academic vision. In this regard, I would like to express my sincere appreciation to our core coordinator team, Professor Ravindra Revaskar, Organizing Secretary, and Dr. Nitin Suradkar, Treasurer, Their tireless efforts, dedication, and leadership form the strong foundation of this conference. I also extend my heartfelt thanks to our anchoring team, led by Dr. Dimple Mapari, Dr. Manoj Malpani, Dr. Nisha Varade, Dr. Jayashree Sakarkare, Dr. Archana Khandelwal, Professor Aditi Mankar, and Ms. Siddhi Waghare for ensuring the smooth flow of the program and keeping the audience engaged throughout the session. With regard to logistics and support, I sincerely appreciate the efforts of all the committee coordinators and their dedicated team members. From registrations and technical support to stage decoration and warm hospitality, your behind the screens efforts ensures a comfortable and memorable experience for all our guests and participants. Finally, I extend my wholehearted thanks to all the researchers, paper presenters, and poster presenters from various institutes. Your scholarly contribution and active participation truly transform this conference into a vibrant hub of innovation and knowledge exchange. I thank everyone who is directly or indirectly contributed to the success of CSAIMS 2026. And I sincerely hope that the deliberations and outcomes of this conference will inspire further research, innovation, and collaboration in the fields of computer science, AI, and mathematical sciences. With these words, I once again express my heartfelt gratitude to all the formal conclude this memorable academic event. Thank you. Thank you to all of you.
Thank you, madam. The session will conclude with national anthem. For that, I invite Shri Sanjay Patil and request everyone to stand up for the anthem.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल वंग विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंग तव शुभ नामे जागे तव शुभ आशीष मागे गाये तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे भारत माता की
With the permission of President, this valedictory session is over.